Our cosmic attic is overflowing with forgotten treasures. For decades, our most powerful telescopes and deep space probes have been collecting information, storing it away in vast digital archives. We have treated these records like old photo albums, a history of what we have already seen, but that view is changing completely. A quiet revolution is happening in astronomy and planetary science, one powered not by new rockets, but by new eyes. Scientists armed with artificial intelligence, sharper algorithms, and simply a fresh perspective are returning to these old datasets. They are making profound discoveries, finding planets, galaxies, and cosmic phenomena that were there all along, hidden in plain sight. By the end of this exploration, you will understand how the future of space discovery is being rewritten by our past. We will uncover a planet that slipped through the cracks of the most famous telescope, witness a stellar explosion that defied classification for years, and even find clues to ancient cataclysms at the heart of our own galaxy. This approach transforms every past mission into a gift that keeps on giving, maximizing our investment and guiding our next giant leap. So what do you believe is still waiting to be found in the data we have already gathered? One of the most striking examples of this archival revolution is a world that was always there, a planet hiding within the most celebrated exoplanet dataset ever compiled. The Kepler Space Telescope observed the same patch of sky for 4 years, its unblinking eye capturing the tiny, rhythmic dimming of stars as planets passed in front of them. Scientists processed this torrent of data, identifying thousands of new worlds, yet the sheer volume was overwhelming, and subtle signals could be easily missed by even the most sophisticated automated filters of the time. Years later, researchers applied new, more sensitive algorithms to the old Kepler data, algorithms trained to spot the faintest whispers in the starlight. And in that re-examination, they found it. A previously overlooked dip in the brightness of a star revealed a planet roughly 1.5 times the size of Earth, orbiting within its star's habitable zone, that region where liquid water could theoretically exist on a rocky surface. This world had been there in the numbers all along, a ghost in the machine waiting to be seen. Its discovery did more than just add another planet to the catalogue. It subtly shifted the statistical landscape, suggesting that potentially habitable, Earth-sized worlds might be even more common than we had calculated from the initial Kepler results. A single overlooked signal once found recalibrated our cosmic senses. This is the power of a second look, the profound truth that our first answer is rarely the final one. But sometimes the secrets in the archive are not about new worlds, but about the oldest building blocks of our own cosmic neighborhood. For decades, the Hubble Space Telescope has been our premier eye on the universe, capturing breathtaking images of distant galaxies and nebulae. Yet some of its most profound discoveries are not in the deep field, but in the seemingly quiet corners of our own galactic backyard. Astronomers recently performed a meticulous digital excavation, sifting through old Hubble images that were originally taken to study other, brighter objects. In the faint halo of stars surrounding our Milky Way, they found a ghost. It was an ultra-faint dwarf galaxy, a wisp of ancient stars so dim and spread out that it had been completely washed out by the glare of its surroundings in every previous survey. This galaxy is a fossil, a relic from the universe's infancy that has been orbiting our own for billions of years. Finding such a faint object is not just about adding another pin to the galactic map. These fossil galaxies are the purest tests we have for our theories of how all galaxies, including giants like the Milky Way, are built. According to our models, large galaxies grow by consuming smaller ones over cosmic time. The surviving ultra-faint dwarfs are the leftovers, the untouched building blocks that never got swallowed. By studying their motions and their incredibly sparse stars, scientists can trace the gravitational scaffolding of dark matter that must be holding them together. Each one is a natural laboratory, offering a unique snapshot of the conditions in the early universe and providing crucial clues about the mysterious, invisible dark matter that shapes everything we see. So a forgotten speck of light in an old image becomes a key to understanding the very formation of our home galaxy and the hidden architecture of the cosmos. Radar echoes from the past hold their own kind of ghost. For years, astronomers have used powerful radar stations to ping nearby asteroids, painting a picture of their shape and surface with radio waves. The data from these observations, often complex and grainy, is archived for future study. One such dataset from a close pass by an asteroid named something like Antiope initially presented a confusing signal. The radar return was smeared and elongated, difficult to interpret with the tools of its time. It was filed away as an oddity, a rock with a peculiar shape. Decades later, with vastly improved computing power and image processing techniques, a team decided to revisit that raw radar echo. They applied new algorithms capable of teasing out incredible detail from noise, effectively giving the data a set of digital glasses. What emerged was not a single, misshapen world. The blur resolved into two distinct points of light dancing around a common center of gravity. They had not been looking at one asteroid, but two. They had rediscovered a binary system, a tiny double planet where a moon orbits its primary body. This was not just a correction in a catalogue. Resolving the two bodies clearly allowed scientists to finally calculate the system's mass and, by comparing it to its size, determine its density. That single number, density, is a Rosetta Stone for understanding an asteroid's composition. Is it a solid chunk of metal, a loose pile of rubble, or something in between? The answer tells the story of the asteroid's formation, whether it was born from the shattering collision of two larger bodies or has held together since the solar system's dawn. A once ambiguous signal, seen with new eyes, transformed into a fundamental clue about the building blocks left over from our planetary construction site. The Sun keeps its own secrets in a silent archive of light. For over 2 decades, instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory have captured nearly every flicker and flare from our star, amassing a visual record of its dynamic life. Scientists recently decided to comb through this entire history with fresh, automated eyes, searching for events that might have slipped past human analysts. What they found was not a missing flicker, but a missing explosion. Buried in the data was evidence of a coronal mass ejection of staggering power, an eruption that had somehow gone unclassified for years. It was not a subtle event. The reason it was missed is a lesson in the limits of our tools. The eruption occurred so close to the Sun's limb, the very edge of the observatory's view, that its full structure was partially hidden. Furthermore, its initial flash was so intensely bright that it temporarily overwhelmed or saturated the sensors designed to measure it. To the algorithms of the time, it looked like an error, a glitch in the matrix, and it was automatically filtered out and forgotten. This was a ghost in the machine of our own making. The implications of finding it now are profound for our understanding of space weather. These coronal mass ejections are billion-ton clouds of magnetized solar plasma launched into space. When they are directed at Earth, they can spark brilliant auroras, but they can also induce powerful electrical currents in our power grids and disrupt satellites and communications. Our models for predicting their impact are built on a catalog of past events. If an eruption of this magnitude was absent from that catalog, it means our historical baseline was incomplete. We have been practicing for solar storms with an incomplete list of the worst-case scenarios. Finding it now allows researchers to feed its true characteristics back into their simulations, refining how we forecast the Sun's temper and better preparing our technology for the day a storm of that scale is aimed directly at us. A single overlooked flash in old data quietly makes our future on Earth a little safer. A different kind of ghost haunts the radio static of the cosmos. In 2007, a powerful radio telescope was conducting a routine survey, its massive dish collecting the faint whispers from deep space. The data was recorded, processed for its intended purpose, and eventually filed away into a vast digital archive. Years later, a student was sifting through this old dataset, training an algorithm to search for unusual patterns. That is when they saw it. A single spike, a burst of radio energy so intense it stood out starkly against the cosmic background noise. It lasted only milliseconds, a blip in the endless stream of data. The most puzzling part was that it never happened again. This was a one-time event, a brilliant flash with no echo, no follow-up, and no obvious source in the sky. It became known as the Lorimer burst, named for the astronomer who led the team that found it. For years, this solitary signal sparked intense debate. Could it have been a glitch, some terrestrial interference like a passing satellite or even a microwave oven in the observatory's kitchen? Or was it the first detected member of an entirely new class of cosmic phenomenon? The mystery lay in its loneliness. True scientific discovery often requires verification, the ability to see something again and again. A signal that appears only once defies that process, leaving it in a frustrating limbo between groundbreaking discovery and curious anomaly. This single point of data became a riddle that would take nearly a decade to begin unraveling, forcing astronomers to question what else might be hiding in the radio archives, waiting for a patient eye to give it a name. The isolation of that single radio burst forced a fundamental question. If one signal could be hiding in old data, how many other cosmic patterns have we simply failed to see because we lack the right perspective? Sometimes the pattern is not hidden in a single, brilliant flash, but woven across thousands of separate moments, waiting to be stitched together into a new kind of vision. This is precisely what happened with our neighboring world, Mars. For decades, orbiters like Viking and the Mars Global Surveyor have been dutifully snapping pictures of the red planet, frame by frame, year after year. Each image was studied for its immediate purpose, to map a canyon or track a local dust cloud, and then stored away. The archive became a colossal, disjointed photo album of a world in motion. Recently, scientists decided to do something unprecedented. They gathered hundreds of thousands of these individual images, some decades old, and fed them into powerful new processing software. The goal was not to look at any single feature, but to combine them all into a seamless, high-resolution movie of the entire Martian atmosphere over time. Think of it as taking every single weather satellite photo of Earth from the past 40 years and assembling them into one continuous global time-lapse. The result was the first true climate map of another world. By stitching this planetary quilt together, researchers could finally watch the long-term rhythms of Mars unfold. They observed how dust storms, which appear as localized tan plumes in any single image, actually follow planet-wide cycles, growing from small gusts into global events that can engulf Mars for months. They tracked the subtle, seasonal expansion and retreat of the polar ice caps with new precision, revealing how much frozen carbon dioxide and water exchange with the thin atmosphere each year. Most importantly, they could see the atmospheric dynamics, the wind patterns and temperature flows that drive these changes, playing out over decades rather than days. This archival weather map transformed Mars from a series of snapshots into a living, breathing system with its own history. It allows scientists to run climate models on another planet and check their predictions against decades of real, observed data. Understanding these long-term cycles is not just academic. It tells us about the stability of the Martian environment, which is crucial for planning the safety of future robotic missions and one day human explorers. A dusty, decades-old archive of images has given us the forecast for another world. That same principle of seeing the whole picture applies to worlds far colder than Mars. On the dwarf planet series, the largest object in the asteroid belt, the Dawn spacecraft spent years in orbit, mapping its gray, cratered surface in exquisite detail. The mission was a triumph, revealing a world surprisingly rich in water, ice, and salts, with one particularly mysterious bright spot in a crater named Arecibo. Scientists identified what they believed was a single large cryovolcano, a mountain named Ahuna Mons, built not from molten rock but from a slow ooze of salty, muddy ice. The primary mission concluded and the vast dataset was archived, a complete atlas of a new world. Yet the story was not finished. Years later, planetary scientists returned to those topographic maps and mineral spectra with a new question. If Ceres had the ingredients and the internal warmth for one cryovolcano, could there be others, perhaps older and more eroded, hiding in plain sight? They applied advanced new analysis techniques, algorithms that could cross-reference subtle shape signatures with precise chemical fingerprints in the data. A rounded dome might look like an old impact scar, but if the composition of that dome matched the unique briny mixture of Ahuna Mons, it told a different story. This digital re-examination revealed not one, but over 30 of these cryovolcanic structures scattered across Ceres. They were the ghosts of ancient eruptions, their once steep slopes softened over billions of years by the dwarf planet's weak gravity, slowly relaxing like a forgotten mound of soft clay. The discovery fundamentally changed our understanding of Ceres' geological life. It was not a dead, frozen relic, but a world that had been quietly active for much of its history, its internal ocean occasionally finding a way to the surface. This has profound implications in the search for the building blocks of life. These cryovolcanos are not just geological curiosities, they are natural deep-freeze archives. The slow, cold eruption of briny material from a subsurface ocean could have transported and preserved complex organic molecules, the kind that serve as life's precursors, from a warm, watery interior to the stable, frozen surface. Finding them now means we know exactly where to look on future missions, marking these gentle domes as priority sites to search for preserved organic material. A reanalysis of old data did not just add dots to a map, it identified the filing cabinets where Ceres may have stored its most ancient and promising chemistry. Sometimes the most massive discoveries are the ones you cannot see at all. This paradox lies at the heart of a ghostly structure found not with optical telescopes, but in the silent, high-energy archives of X-ray observatories. For years, the Chandra X-ray Observatory and XMM-Newton have been studying nearby spiral galaxies, their instruments tuned to detect the faint glow of multimillion-degree gas. The data was clear for the bright, active cores of these galaxies, but the outer regions seemed quiet, just empty space. The story, however, was hidden in the noise. Scientists realized that the signal of a faint, diffuse halo of hot gas around a galaxy like our own Milky Way would be incredibly subtle, buried beneath background X-ray static and instrumental interference. To find it, they turned to a technique not unlike stacking hundreds of faint, noisy photographs to bring out a hidden image. They gathered archival X-ray data not from one galaxy, but from dozens of similar spiral galaxies. Then they carefully aligned all the images, stacking them on top of each other. By doing this, the random noise averaged out, while the consistent, whisper-thin signal of the hot gas in the galactic halo reinforced itself, slowly emerging from the digital fog. What appeared was a breathtaking and colossal structure, an enormous, faint sphere of superheated gas enveloping the entire galaxy, extending hundreds of thousands of light-years into what was thought to be empty intergalactic space. This was not a small feature, it was a giant's breath, a vast atmospheric envelope holding more normal matter or baryons than all the stars in the galaxy itself. Its discovery solved a long-standing cosmic puzzle known as the missing baryon problem. Our models of the Big Bang predict how much normal, atom-based matter should exist in the universe. Yet, when we counted all the stars, planets, gas clouds, and dust we could see, the numbers did not add up. A huge portion of the universe's expected ordinary matter was simply unaccounted for. This newly revealed galactic halo, this reservoir of incredibly hot, thin gas, appears to be where a significant fraction of that missing matter has been hiding all along. It is the hidden atmosphere of galaxies, a record of their most violent pasts. This gas is likely heated to such extreme temperatures by the colossal energy of supernova explosions over billions of years, a continuous outflow that shapes the galaxy's evolution by regulating how fast new stars can form. Finding it required seeing not just a new object, but an entirely new way to look, transforming background noise into a fundamental map of a galaxy's extended life, and finally balancing the universe's ledgers with matter we had always possessed but never truly seen. The universe writes its history in passing lights, and sometimes we only read the footnote after the chapter has closed. This was the case for our first known interstellar visitor, the enigmatic object named Oumuamua. When it was first detected in 2017, it was already speeding away from the Sun, a faint point of light on a trajectory that screamed it was not from here. The initial observations were frantic, a scramble to characterize something utterly alien before it vanished forever into the dark. Its bizarre shape, its lack of a visible coma like a comet, and its unexpected acceleration made it a sensation and a profound puzzle. But the story of understanding Oumuamua did not end when it faded from view. In fact, that is when a different kind of search began, a digital archaeology project in humanity's own records. Astronomers around the world turned their attention not to the sky, but to their hard drives. They began combing through terabytes of archived images from automated sky surveys that had scanned the same patch of space in the weeks and months before Oumuamua's official discovery. They were hunting for a ghost, a precovery. This is the term for finding an object in old data after its current existence is known. It is like finding a stranger in the background of your vacation photos from last year, only realizing they were there once you have met them today. And they found it multiple times, in images from telescopes as far back as several weeks prior to the alert. There it was, a faint dot that every automated system had ignored because it was just one of millions. But now, with the precise trajectory calculated from its later discovery, astronomers could trace its path backwards with pinpoint accuracy and see it had been there all along. These precovery observations were not just a cosmic "I told you so." They were transformative. Each additional data point, especially those from earlier in its journey through our solar system, acted like a surveyor's stake, allowing scientists to triangulate its path with far greater precision. They could now calculate its approach trajectory from interstellar space with a new level of confidence, ruling out some potential home stars and suggesting others. More subtly, by measuring its brightness in these earlier images and comparing them to later ones, researchers could better chart its tumbling rotation. They confirmed it was not spinning in a simple, stable way, but tumbling chaotically like a bottle tossed from a ship, a motion that hinted at a violent past, perhaps involving a collision in its home system. This archival detective work tightened the constraints on what Oumuamua could be. The refined trajectory made its interstellar origin undeniable. The detailed rotation analysis helped rule out some of the more exotic explanations for its acceleration, leaning the consensus toward a natural, if unusual, object, perhaps a fragment of a Pluto-like world or a dust-free comet releasing hidden gases. Those forgotten points of light in old survey images turned a fleeting mystery into a more solid data point in our cosmic address book, proving that even for a visitor that did not stay, its story was partially written in our own archives, waiting to be read. The moon holds its own pale mysteries, written not in words, but in ghostly light and invisible force. For centuries, astronomers have noted strange, bright, swirling patterns on the lunar surface, elegant curls and walls that look like cream stirred into dark coffee. These features, called lunar swirls, stood out starkly against the dark gray plains, but their origin was a complete enigma. They did not match any known crater or mountain range. They seemed almost painted onto the landscape. For a long time, the best guess was that they were the faint scars of ancient comet impacts, but the evidence was thin. The real breakthrough would come not from a single new image, but from a marriage of two different archives separated by decades. In the late 1990s, a small spacecraft called Lunar Prospector orbited the Moon, equipped with a sensitive magnetometer. Its mission was to map the Moon's surprisingly weak and patchy magnetic field, a relic of its ancient geologic past. It collected a global dataset of these magnetic anomalies, which was studied, published, and then stored away. Years later, the Lunar Reconnaissance Orbiter arrived, armed with cameras of incredible sharpness. It began capturing the entire lunar surface in stunning, high-resolution detail, creating a new atlas where the swirls could be seen with crystal clarity. Independently, each archive told an interesting but incomplete story. One was a map of invisible magnetism, the other was a photo album of visible, puzzling beauty. The revelation occurred when scientists decided to lay one map perfectly over the other. They aligned the decades-old magnetic data from Lunar Prospector with the new, detailed images from the Reconnaissance Orbiter. The correlation was astonishingly precise. Every single major bright swirl on the Moon sat directly on top of a local, strong magnetic anomaly. It was not a vague association. The swirling shapes themselves seemed to trace the outlines of these invisible magnetic bubbles embedded in the lunar crust. This was the crucial clue. The leading theory now had a solid foundation. The Moon has no global atmosphere to shield its surface from the constant stream of charged particles flying from the Sun, known as the solar wind. This relentless bombardment slowly darkens the lunar soil over millions of years, a process called space weathering. However, these localized magnetic fields act like miniature shields. They deflect the solar wind particles, preventing them from hitting the soil directly beneath. The protected soil retains its original, brighter color, while the surrounding area slowly darkens. Over eons, this creates the stunning, bright swirls we see, a direct imprint of an invisible magnetic architecture on the visible landscape. This discovery did more than solve a pretty puzzle. It revealed that the Moon's ancient magnetic history is not just a faded global memory, but is still actively writing on the surface today, shaping its appearance in real time through its interaction with the Sun. It transformed the swirls from static art into a dynamic record, a testament to how the past continuously sculpts the present, all revealed by connecting two different chapters in our lunar archive. The most violent explosions in the universe leave their signatures in a fleeting archive of light. For over 30 years, satellites like the Compton Gamma Ray Observatory and the Fermi Gamma Ray Space Telescope have been silently logging these cosmic cataclysms known as gamma ray bursts. Each one is a digital firework, a spike of unimaginable energy that appears, fades, and is catalogued by its duration and brightness. The data piles up, and with thousands of events, the focus naturally falls on the clear, strong signals that fit established patterns. But what about the odd ones, the bursts that do not quite match the template? A recent deep dive into this high-energy archive focused on precisely these outliers. Researchers returned to decades of Fermi data, applying new analytical filters designed to catch subtleties the initial processing might have missed. Their search highlighted one particular burst from several years prior. On the surface, it was unremarkable, a medium-length flash. But when they isolated and magnified its very first milliseconds, they found something extraordinary. Nestled within the data, preceding the main explosion by a mere heartbeat, was a tiny, distinct flicker of gamma rays. It was a precursor, a whisper before the scream. This was not part of the standard model. According to leading theories, the longest gamma-ray bursts are thought to be caused by the collapse of a massive star's core into a black hole, a process that should be a single, catastrophic event. The presence of a clear, separate precursor signal challenges that simple narrative. It suggests the collapse might have stages or that the star's interior structure was more complex than we assumed. Perhaps magnetic fields within the dying star snap and reconnect moments before the final plunge, releasing a warning flash. Or maybe it hints at a different mechanism entirely, like a neutron star being dragged into a black hole and flaring as it is torn apart. This single, overlooked blip in old data forces theorists to refine their simulations. They must now account for a scenario where the universe's most powerful detonations might announce themselves, however faintly, before the main event. That tiny archival signal transforms a single explosion from a statistic into a crucial clue, pushing our models of stellar demise to be more nuanced, reminding us that even in death, stars may have more than one story to tell. The ghostly whispers of a dying star remind us that even the most fleeting signals can rewrite our cosmic textbooks. But what about the slow, patient transformation of a world, a story told not in milliseconds but over entire seasons? To find that narrative, we must look to the edge of our solar system, to a small, cold world whose brief visitor left behind a puzzle. When the New Horizons spacecraft raced past Pluto in 2015, it was a blur of frantic activity. For a few precious hours, every instrument on board drank in as much data as possible, a single snapshot of a complex world before the probe sped away forever. The initial analysis was a triumph, revealing towering mountains of water ice and vast plains of frozen nitrogen. But the story of Pluto's thin, hazy atmosphere was particularly tricky. The data was there, measurements of its composition, pressure, and structure, but understanding its behavior was like trying to deduce an entire year's weather from a single afternoon's observation. For years, that single snapshot was all we had. Then, scientists decided to give that static picture motion. They returned to the raw atmospheric data from the flyby and fed it into powerful new climate models, computer programs vastly more sophisticated than those available a decade prior. These models could simulate how Pluto's atmosphere evolves over its 248 Earth-year orbit, accounting for the extreme seasonal shifts as it moves from a closer perihelion to a more distant aphelion from the Sun. Applying these new digital lenses to the old measurements revealed a world in constant, dramatic flux. The models suggested that what New Horizons saw was not Pluto's average state, but a specific moment in a long climatic cycle. The atmospheric pressure at the surface, for instance, was likely much higher in the decades before the flyby, and is now predicted to be collapsing as the dwarf planet moves further from the Sun's faint warmth, causing the nitrogen in its atmosphere to slowly freeze back onto the surface. This revised understanding of the escape rate, how quickly gases are lost to space, was equally profound. Initial estimates were recalibrated, suggesting the process is more nuanced and seasonally driven than a simple, constant leak. Perhaps the most visually striking correction came from the haze. The original images showed Pluto enveloped in beautiful, blue layers of atmospheric haze, but the new analysis of the scattering of sunlight within that data indicated these layers were far more extensive and complex than first thought. They are not a passive veil, but an active chemical factory. As ultraviolet light from the distant sun breaks down methane high in the atmosphere, it triggers the formation of complex hydrocarbons, which then clump together into tiny Tholen particles, giving the haze its reddish color and eventually snowing down to stain Pluto's surface. This refined view transforms Pluto from a frozen portrait into a dynamic system. Its atmosphere breathes, expanding and contracting with the seasons. Its sky is an ongoing chemical experiment, painting the landscape below. That one frantic flyby dataset, when re-examined with the right questions and better tools, stopped being a mere photograph and started playing like a movie, showing us a small, distant world with a surprisingly active and rhythmic life of its own. A faint star winked out, and in that brief darkness a solar system was rewritten. Far beyond the orbit of Neptune, in the cold, chaotic realm of objects known as centaurs, something impossible was waiting to be seen. These minor planets, named for mythical hybrids, orbit between Jupiter and Neptune and are thought to be icy refugees from the Kuiper belt. For decades, they were seen as lonely wanderers, simple lumps of rock and ice. But in 2013, astronomers were preparing to observe a stellar occultation by one of the largest centaurs, an object called Chariklo. They trained their telescopes on a distant star, waiting for Chariklo to pass in front of it and block its light. The star's dimming would reveal the object's size and shape. What happened instead was a sequence of events so precise and strange it seemed like a mistake. The star's light did not simply vanish and reappear, it flickered. Just before the main occultation, the starlight dipped briefly, then it dipped again just after the main event. It was as if something else, something on either side of the main body, was also blocking the star. The data was clear and repeatable across multiple telescope sites. The only plausible explanation was as breathtaking as it was unexpected. Chariklo was not alone. It was surrounded by two thin, dense rings. This was a discovery that shattered paradigms. Rings were the majestic signature of giant planets, the iconic feature of Saturn. Finding a complex ring system around a tiny, 150-mile-wide object was like finding a fully formed city on a solitary asteroid. It forced an immediate and profound question. How could such a small, weak gravitational field hold onto rings? The material should either drift away or clump together into a moon within just a few thousand years. Their existence meant they were either very young, the result of a recent catastrophic collision, or they were being actively shepherded and confined by unseen, tiny moonlets orbiting just beside them. The Chariklo data was a revelation, but it was a single snapshot. To understand the ring's stability, their shape, and whether other centaurs had them, scientists needed more data. They turned to the archives. Occultations are chance events predicted years in advance. But what about the past? For decades, professional and amateur astronomers worldwide have been recording occultations, building a vast, scattered library of light curves, graphs of a star's brightness over time. The team began a digital treasure hunt, searching through old records for any past occultations by Chariklo or its cousin, the centaur Chiron. They found several. By combining these multiple archival light curves, each from a different viewing angle as the Earth moved, they could perform a kind of cosmic tomography. It was akin to doctors combining many two-dimensional X-rays to build a three-dimensional model of a body. Here, they combined many one-dimensional slices of starlight to reconstruct the two-dimensional shape of the rings from different angles. This archival stitching revealed the rings were not only real, but they were narrow, sharp-edged, and possibly elliptical, shaped by the gravitational tug of those hypothesized shepherd moons. This methodology changed everything. It proved that the careful, long-term work of amateur astronomers, often filed away in obscure databases, could be combined with professional analysis to make landmark discoveries years after the fact. A centaur was no longer just a distant speck. It was a miniature planetary system, a fragile, elegant relic holding onto its own delicate architecture against all odds, its secrets preserved in the forgotten flicker of stars recorded long ago. Deep within the cosmic nurseries of dust and gas, a hidden generation of stars was just beginning to stir. For 16 years, the Spitzer Space Telescope peered into these murky stellar wombs using its infrared eye, seeing the warm glow that visible light telescopes could not. It mapped entire molecular clouds, cataloging thousands of bright, obvious young stars. Yet within that immense archive, a subtler population remained invisible, their faint heat signatures drowned out by the brilliant infrared noise of the dusty clouds themselves. It was like trying to hear a whisper in a roaring stadium. Recently, astronomers trained a new kind of listener on this old data. They developed sophisticated machine learning algorithms, not to find what we already knew, but to recognize the unique, faint fingerprint of an object so young it has not truly become a star yet, a protostar in its earliest, most embedded phase. These algorithms sifted through the infrared noise pixel by pixel, learning to distinguish the specific, subtle warmth of a collapsing core of gas from the general background heat of its dusty surroundings. The result was a quiet census of the unseen. In clouds we thought we knew well, like those in the constellation Orion, the algorithms revealed dozens of these infant protostars that every previous survey had missed. They were not yet shining from nuclear fusion in their cores, but were glowing faintly from the sheer gravitational energy of their collapse, cocooned so deeply in their birth clouds that not even infrared light could escape cleanly. This discovery does more than just add new dots to a star map. It forces a recalibration of a fundamental cosmic clock, the star formation rate. If we have been missing this entire earliest phase of stellar birth in our tallies, then our estimates of how many stars are being born in these clouds and how quickly have been significantly undercounted. A molecular cloud we classified as middle-aged with its obvious young stars already shining might actually be far more active and fertile than we thought, still bustling with these hidden newborns. This changes our timeline for how these stellar nurseries evolve and eventually dissipate. By finding the missing first chapter in the archival data, we get a truer picture of the life cycle of stars, understanding that the birth of suns is a more continuous and perhaps more prolific process than our initial snapshots suggested. A faint chemical signature, dismissed for years as background noise, has finally been heard. The Curiosity rover has been sniffing the thin Martian air since its landing, using an instrument called the tunable laser spectrometer to detect minute traces of gases. For a long time, its most tantalizing and frustrating readings concerned methane. On Earth, the vast majority of methane is produced by living organisms, making it a potential biosignature, a chemical whisper of life. The rover did detect occasional, tiny spikes of the gas, but they were so small and sporadic that many scientists argued they could be statistical flukes, or perhaps even contamination from the rover itself. The data was archived, the debate simmered, and the mystery remained open. Then, a team decided to re-examine every single methane measurement with a new, more rigorous statistical model. They treated the entire dataset not as a collection of individual readings, but as a continuous story, applying filters that could better distinguish a true Martian signal from the instrument's own inherent electronic noise. This refined analysis reached a startling conclusion. One particular spike, previously brushed aside as unreliable, was in fact statistically significant. It was real, the methane had been there. This was not a one-time event either. The new analysis suggested a pattern, a faint but repeating rhythm to the methane's appearance in the Gaia crater. The implications are profound because methane should not last long in the Martian atmosphere. Solar radiation and chemical reactions should break it apart within a few hundred years. So if methane is present now and reappearing in cycles, something on Mars must be producing it or releasing it in the modern era. That source could be geological. Certain rock-water interactions, like a process called serpentinization, can produce methane abiotically without any life involved. It could also be biological, the product of subsurface microbial communities metabolizing in hidden reservoirs. The new certainty of the detection does not tell us which it is, but it dramatically sharpens the question. It transforms methane from a maybe into a definite clue, a puzzle piece that future missions, like the ExoMars rover with its dedicated drill, are now specifically designed to investigate. That once dismissed data point now acts as a compass, pointing our next robotic explorers to dig deeper, to follow the chemical trail that begins with a ghost in the machine's own readings. That chemical whisper on Mars is a clue written in the atmosphere, but some of the universe's most important writing is completely invisible. To map the unseen architecture of the cosmos, astronomers have learned to read the distortions in light itself, a technique known as gravitational lensing. When a massive object like a galaxy cluster sits between us and a more distant galaxy, Its immense gravity warps the fabric of space-time, acting like a cosmic magnifying glass. It bends and distorts the light from the background galaxy, often stretching it into long, faint arcs or even multiple images. For years, the Hubble Space Telescope has captured thousands of these spectacular lensing events within galaxy clusters, creating a stunning archive of warped light. The initial analyses of these images were groundbreaking, using the distortions to roughly map the cluster's total mass, both visible stars and the dominant, invisible dark matter. But those first maps were like seeing a mountain range from a distance, understanding its general shape but missing all the intricate ridges, valleys, and hidden canyons. The true, fine detail of the dark matter landscape within these clusters remained blurred. Recently, teams of researchers returned to Hubble's deep archives with a new generation of gravitational lensing models, algorithms of unprecedented sophistication. These new tools did not just look for obvious giant arcs, they could detect and measure the most subtle shearing, the tiniest stretching of thousands of faint background galaxies seen through the cluster's outer regions. By processing this old light with these new eyes, they constructed dark matter maps of staggering resolution. The resulting charts revealed the invisible scaffolding in exquisite detail, showing how dark matter is not just a smooth, featureless halo enveloping the cluster. Instead, the maps unveiled a rich substructure with dense clumps and filaments of dark matter intertwined with the visible galaxies and vast, diffuse bridges connecting massive cluster cores. This level of detail is not just a prettier picture, it is a critical test for our most powerful supercomputer simulations of the universe. Cosmologists run vast virtual universes governed by our current understanding of physics and dark matter, to see how large-scale structure forms over billions of years. The predictions these simulations make about the distribution and clumpiness of dark matter can now be compared directly to these new, empirical maps from the Hubble archive. It is a reality check on our most fundamental theories. Do the simulated dark matter halos have the same intricate internal structure as the real ones we can now infer? Early comparisons show remarkable agreement, but also hint at subtle differences in how clumpy the dark matter is on small scales. These tiny discrepancies are not failures, they are guides. They may point toward deeper properties of dark matter itself, suggesting whether it is cold, warm, or interacts with itself in ways we have not yet considered. A decades-old photo album of bent light, reanalyzed, has given us the most precise blueprints yet of the universe's hidden framework, turning each lensing cluster into a natural laboratory where we can finally watch dark matter dance. A faint, almost decorative smudge on the edge of a world caught someone's eye. It was a day like any other for a planetary scientist browsing the public image archives from the Galileo mission to Jupiter. They were not studying volcanism that day, but something about a particular frame of Jupiter's tortured moon Io gave them pause. The image was a wide-angle shot, intended to capture the context of the Jovian system, with Io appearing as a crescent against the black of space. There, right on the moon's sunlit limb, was a tiny, feathery projection. It was not a camera artifact nor a scratch on the lens. It was a volcanic plume erupting from a vent that had never been catalogued, caught in a moment of violent beauty in an image that was never meant to look for it. This was not the work of automated software or a dedicated observation campaign. It was a pure human discovery, the result of curiosity and a patient gaze upon old data. The researcher immediately knew the significance. Io, stretched and heated by the immense gravitational tides of Jupiter, is the most volcanically active body in the solar system. Its surface is a constantly changing map of lava lakes and sulfurous deposits. Finding a new vent is like finding a new geyser in Yellowstone, a fresh outlet for the moon's internal fury. The team went back through the archive, searching for other images of that same region from different flybys and different angles. By triangulating the plume's location with other datasets, they pinpointed the exact source, a previously anonymous patch of terrain now marked as an active volcanic center. This discovery did more than add another dot to Eo's fiery map. It served as a powerful reminder of the limitations of even our most targeted scientific missions. We send spacecraft with specific goals and observation plans, but the universe is always performing, always offering data points outside the script. A camera pointed at Jupiter for a context shot inadvertently became a volcano monitor. It proved that on a world as dynamic as Io, any single snapshot is just that, a single frame in a non-stop film. The plume on the limb, a chance capture in an old archive, underscored that some of the most active processes in our solar system can still hide in the margins, waiting for a viewer to look not just at the intended target, but at the entire story the picture has to tell. Sometimes the brightest objects in the sky create the most perfect hiding places. This paradox was at the heart of a discovery made not by peering into the void, but by looking away from the light. For years, the Hubble Space Telescope had captured stunning images of a brilliant globular cluster, a dense swarm of hundreds of thousands of ancient stars all orbiting the core of a nearby galaxy. The cluster was the obvious subject, a glittering jewel for astronomers to study. The data was processed, the cluster's stars were analyzed, and the files were archived. Yet all that brilliance created a problem. The combined glare from these tightly packed stars washed out everything in their immediate vicinity, like trying to see a firefly resting on a lit light bulb. The surrounding space was assumed to be empty, a blank canvas behind the stellar spectacle. But a team of researchers had a different idea. They wondered if the techniques used to find faint planets around bright stars could be applied on a galactic scale. They returned to the Hubble archive and retrieved the original, raw images of that glittering star cluster. Their goal was not to study the cluster itself, but to meticulously remove it. Using sophisticated software, they modeled and digitally subtracted the precise light profile of every single one of those hundreds of thousands of foreground stars. It was a painstaking process of peeling back a layer of the universe, like carefully wiping fog from a window. What they revealed behind the stellar glare was not empty space. There, spread across the field of view, was an enormous, gossamer, thin smudge of light. They had uncovered an ultra-diffuse galaxy, a class of galaxy so faint and spread out it had been completely invisible beneath the cluster's radiance. This ghostly galaxy was as large as our own Milky Way, but its stars were scattered so thinly that it emitted only about 1% of the light. Finding it in such a crowded environment was a profound surprise. Astronomers had believed these ultra-diffuse galaxies were primarily orphans, floating alone in the quiet voids between galaxy clusters, where the gentle environment allowed their delicate structures to persist. The discovery of one hiding literally within the blinding light of a dense star cluster shattered that assumption. It proved these faint giants could form or survive in the most unexpected and crowded places. This forces a re-evaluation of their origins. Perhaps they are failed galaxies, born with too little gas to ever form many stars. Or maybe they are the stripped and stretched remnants of once normal galaxies that had all but their most loosely bound stars torn away by gravitational encounters. Its presence in the archive, hidden behind a curtain of light, tells us that the universe is still adept at keeping secrets in plain sight, and that sometimes to find something new, you must first learn how to erase what you already know. The most fundamental yardstick in the cosmos just got a quiet recalibration. For a century, we have known the universe is expanding, and the rate of that expansion is encoded in a single, critical number called the Hubble constant. To measure it, astronomers rely on cosmic mile markers, especially the brilliant explosions known as Type Ia supernova. These stellar detonations are so consistent in their peak brightness that they are called standard candles, allowing us to gauge vast distances across the universe. For decades, telescopes have been collecting the light from these supernovae, building an archive of their brilliance and their redshift, which tells us how fast their host galaxy is receding. This data formed the backbone of our cosmic distance ladder, yet a subtle problem was always lurking in the fine print. The instruments that gathered this light, whether ground-based telescopes peering through Earth's shimmering atmosphere or space-based observatories, are not perfect time capsules. Their sensors can degrade minutely over years. The filters that isolate specific colors of starlight can slowly change their transmission properties. Even the models for how Earth's atmosphere absorbs and scatters light have improved. All of these are calibration issues, tiny systematic errors that, if uncorrected, introduce a silent bias into every single measurement of a supernova's true brightness. A recent, meticulous study returned to the original photometric data from supernova surveys conducted in the 1990s and 2000s. The team applied new, refined models of instrument behavior and atmospheric effects to this old raw light data. They were not looking for new supernova, they were remeasuring the old ones with a better ruler. The corrections were minuscule, often fractions of a percent. But when applied across the entire historical dataset and propagated up the cosmic distance ladder, the effect was significant. The recalculated brightnesses of these standard candles led to a subtle but important revision of the Hubble constant. The universe's expansion rate, it seems, is a touch different than we had calculated from the initial, less corrected data. This is not just an academic adjustment. The precise value of the Hubble constant is the cornerstone for calculating the age, size, and ultimate fate of the entire cosmos. Furthermore, a persistent tension has grown in modern cosmology, where measurements of the early universe from the cosmic microwave background suggest a slightly different expansion rate than measurements from supernova and other local markers. This discrepancy might point toward new physics, perhaps a previously unknown form of energy or a flaw in our understanding of gravity. By cleaning the lenses of our past observations, by removing the accumulated dust of instrumental drift, we get a clearer, sharper view of this tension. The revised archival data helps clarify whether the mismatch is a real clue to cosmic secrets or merely a ghost in our own machinery. It proves that even our most fundamental constants are not carved in stone, but are living numbers, refined each time we learn to see our own tools more clearly. Saturn's rings are not a static sheet of ice, but a fluid, dynamic river of countless particles, each following its own silent orbit. For 13 years, the Cassini spacecraft circled the gas giant, its cameras capturing the rings in staggering detail, from their broad, bright divisions down to textures finer than the width of a city. Scientists initially focused on the grand architecture, the sweeping gaps and sharp edges carved by the gravity of larger, known moons like Pan and Daphne's. Yet within the rings themselves, especially in the complex, braided strands of the F-ring, the data held whispers of smaller, unseen sculptors. The challenge was immense, like trying to spot a single pebble shifting the current of a vast, flowing river from a photograph taken miles above. To find them, researchers undertook a monumental digital excavation. They returned to the Cassini archive, compiling not dozens, but thousands of individual images of specific ring segments. By stacking and comparing these images over time, they could watch not just the rings, but the patterns within them. What they were looking for was not a tiny dot, but a gravitational signature. A moonlet only a few hundred meters across is far too small to see directly at such a distance, but its gravity is strong enough to tug on the icy particles around it. As it orbits, it creates what scientists call a propeller feature, a subtle S-shaped disturbance in the ring material, a miniature wake in a sea of ice. Finding these propellers required algorithms that could detect these specific, faint patterns against the ever-shifting background noise of the rings. The painstaking review paid off, revealing not one or two, but entire populations of these embedded moonlets. They are the shepherds of the fine structure, the hidden architects. Their constant, gentle gravitational nudges are what maintain the sharp inner edge of a ring, or prevent a narrow strand from spreading out and dissipating over time. A moonlet's gravity can also create strange, kinked patterns or even temporary clumps as ring particles respond to its pull. This discovery transformed our understanding of ring mechanics. We once saw the rings as a passive decoration, shaped primarily by the large, distant moons. Now we understand they are self-sculpting, their finest details maintained from within by these countless, unseen custodians. Each propeller feature in an old Cassini image is a signature, the only visible trace of a hidden world too small to photograph, yet powerful enough to leave its mark on one of the solar system's most magnificent sights. The faintest dip in starlight can tell a story more complex than the planet itself. While most exoplanet discoveries focus on the transit, the moment a planet crosses in front of its star, there is another, even more subtle signal hidden in the rhythm of the orbit. It happens when the planet moves behind its star, an event called the secondary eclipse. As the planet vanishes, the total light from the system dips by an almost imperceptible amount, equivalent to trying to see a single firefly vanish next to a stadium floodlight. This tiny decrease is the direct fingerprint of the planet's own heat and reflected light. For years, the Spitzer Space Telescope recorded these events for dozens of so-called hot Jupiters, gas giants orbiting perilously close to their suns. The initial data was noisy, the signals buried in the chaotic static of the telescope's own detectors and the stellar variability. Scientists could confirm the eclipses were happening, but pulling clear details about the planet's atmospheres from that noise seemed nearly impossible. The data was archived, a record of whispers deemed too faint to decipher. Then, a new generation of data detectives went to work. They developed advanced noise reduction algorithms, not unlike the sophisticated noise-canceling headphones that can isolate a single voice in a crowded room. These algorithms were trained to recognize and meticulously subtract the specific, repeating patterns of instrumental noise from Spitzer's detectors, patterns that had previously blurred the true astronomical signal. They applied this new digital filter to the old secondary eclipse data for a number of hot Jupiters. What emerged from the cleaned-up data was nothing short of a chemical revelation. For several planets, the refined eclipse depth at different infrared wavelengths revealed the first confident detection of specific molecules in their atmospheres. In one case, the signature of water vapor appeared, a clear absorption dip at a precise wavelength. In another, hints of methane and carbon monoxide emerged from the statistical fog. This was not just about confirming that exoplanets have atmospheres, we knew that. This was about reading their composition from light that had been collected years prior. The implications are profound for understanding planetary evolution and diversity. A hot Jupiter with strong water vapor might have formed farther out in its system and migrated inward, preserving some of its icy heritage. One rich in carbon-bearing molecules like methane suggests a different chemical pathway in its swirling, scorching atmosphere. These archival findings created the first true benchmarks for atmospheric models of alien worlds. Theorists could now test their simulations against actual, detected chemicals, not just hypothetical guesses. Each molecule identified from old data acts as a constraint, forcing models to become more accurate and helping us predict what we might find in the atmospheres of smaller, more temperate worlds in the future. A signal once lost in noise became a definitive line in a distant world's chemical profile, proving that even the data we think we have exhausted still holds undiscovered layers of truth. Its surface color was a puzzle written in faded ink. Far beyond Neptune, in the deep freeze of the Kuiper belt, an object known as something like Quaoar presented astronomers with a confusing portrait. Over the years, various telescopes, both the Hubble Space Telescope in orbit and powerful observatories on the ground, had taken snapshots of this distant world. Each image was captured through different colored filters, designed to measure the specific shades of sunlight reflected from its icy surface. The data was archived, but when scientists initially tried to combine these measurements from different sources and different times, the results were inconsistent. The objects seemed to be different colors depending on which dataset you looked at. It was as if several artists had painted the same landscape, but one used crimson, another used ochre, and a third used a faint blue-gray. For a long time, this inconsistency meant Quaoar's true color, and thus the clues it held about its composition remained murky and debated. The problem wasn't that the data was wrong, it was uncalibrated. The cameras on Hubble age and ground-based telescopes must peer through an ever-shifting atmosphere that tints and scatters light in unique ways. A recent project decided to solve this archival riddle. Researchers gathered every available color measurement from the past 2 decades and subjected them to a rigorous digital reconciliation. They applied new, precise corrections for the aging of Hubble's sensors and created sophisticated models to account for the atmospheric distortion in each ground-based observation. They were, in effect, creating a universal color translator, ensuring every data point was speaking the same chromatic language. When they finally combined this recalibrated data, the object's true hue emerged with new clarity. For Quaoar, the consensus revealed an unexpectedly red surface, a deep, rusty tone stark against the black of space. This is not a mere aesthetic detail. In the outer solar system, color is a direct chemical fingerprint. A bright, blue-white surface typically indicates freshwater ice, pristine and recently exposed. A deep red hue, however, suggests the presence of complex organic compounds called tholins. These are not signs of life, but of its raw ingredients. Tholins form when simple ices like methane and nitrogen are bombarded for billions of years by cosmic rays and ultraviolet light from the distant sun, a slow, cold chemistry experiment that creates reddish-brown, tar-like sludge. Quaoar's pronounced redness tells us its surface is ancient and has been thoroughly processed by this relentless space weathering. It also hints at a history of activity. Some of the reddest known objects in the Kuiper belt, like Pluto's moon Charon, have their color linked to material that has escaped from a more volatile world and settled on their surface. Quaoar is known to have a ring system and even a thin atmosphere of carbon monoxide. Its red color could be a coating that fell from this atmosphere as seasonal frosts, or it could be the native color of its own ancient, irradiated crust. By finally harmonizing the discordant notes in the old archives, we don't just see a color, we read a history book. We see a world that has been sitting in the cosmic deep freeze for eons, its surface slowly cooked by radiation into a complex organic veneer, preserving a record of the primordial chemistry from which our own solar system was made. The solar system's grandest collisions left behind a ghostly afterglow, written not in visible light but in ancient heat. For decades, space-based infrared telescopes like the Infrared Astronomical Satellite and the Cosmic Background Explorer mission have been quietly mapping the entire sky in wavelengths invisible to our eyes. Their primary goal was to study the faint, uniform glow of the cosmic microwave background, the afterimage of the Big Bang itself. To do that, they first had to map and subtract all the local foreground sources of infrared light from distant galaxies to the warm dust within our own Milky Way. This foreground data, a catalogue of cosmic clutter, was set aside in archives once the primary cosmological work was done. Yet within that clutter, scientists suspected, lay a hidden story of our own celestial neighborhood. The challenge was monumental, like trying to hear a single, sustained note played by a violin within a roaring symphony orchestra. The infrared sky is a brilliant, chaotic tapestry of emission from interstellar dust clouds, distant stellar nurseries, and the zodiacal light from dust within our own inner solar system. To find the faint signature of specific asteroid families, researchers needed a new kind of filter. they returned to the all-sky infrared maps with advanced algorithms designed not to find bright objects, but to isolate extremely subtle, diffuse patterns. They were looking for the faint thermal glow of bands of dust so tenuous they are utterly invisible in optical light. By digitally peeling away the brighter, smoother components of the infrared foreground, they revealed something astonishing. Etched across the sky were delicate, looping bands of warm dust, each one tracing the orbital path of a known family of asteroids. These were not random clouds, but precise celestial highways of debris. Each band is a cosmic crime scene, the lingering thermal evidence of a catastrophic breakup that occurred millions of years ago. When a large asteroid is shattered in a collision, the fragments, from mountain-sized chunks down to fine dust, continue to orbit the Sun along roughly the same path as their parent body. Over immense stretches of time, gravitational nudges from planets and the subtle pressure of sunlight, called the Poynting-Robertson effect, slowly cause the finer dust to spiral inward toward the Sun. But before it vanishes, it leaves this detectable infrared smear along its family's orbit. Analyzing these archival dust tracks allows scientists to do forensic astronomy. By measuring the band's thickness and temperature, they can estimate the total mass of dust and the size distribution of particles. This, in turn, tells them about the violence of the original collision. Was it a high-speed shattering that produced fine powder, or a more gentle disruption leaving larger fragments? The bands also act as clocks. The fact that we can still see them means the collisions that created them are relatively recent on an astronomical timescale, likely within the last few tens of millions of years. This gives us a direct measurement of the impact rate in the main asteroid belt during a recent chapter of solar system history. It reveals that our neighborhood is not a quiet, static museum, but an occasionally violent and still evolving construction site where the ghosts of ancient crashes continue to warm the darkness, their stories preserved in the forgotten thermal static of old all-sky surveys. The universe's most precise timekeepers can be hidden by their own motion. Deep within the archives of a major radio observatory, a faint, rhythmic signal had been passing unnoticed for years. It was the data from a routine survey of the galactic plane, a search for the telltale pulses of spinning neutron stars. These stellar corpses, called pulsars, beam radiation like cosmic lighthouses, and their rotations can be astonishingly regular, rivaling the best atomic clocks on Earth. Yet this particular signal was not clean. It was smeared and distorted, its rhythm lost in a chaotic Doppler shift so extreme that it looked like mere static to the standard search algorithms of the time. The pulsar was not alone. It was locked in a ferociously tight orbit with a companion star. As it whipped around its partner at a significant fraction of light speed, its radio pulses were being stretched and compressed by the orbital motion. To the software, it was noise, not a signal. A team of researchers later developed a new search algorithm, one designed to hunt for these hidden dancers. Instead of looking for a steady beat, it was programmed to test for millions of possible orbital speeds and shapes, effectively trying to unwind the Doppler smearing to see if a clean pulse emerged. When they ran this digital detective on the old survey data, the result was immediate. The static resolved into a perfect, rapid tick, a pulse every few milliseconds. They had discovered a millisecond pulsar in a compact binary system, a cosmic metronome that had been swinging through space for years, its rhythm masked by its own dizzying dance. This was more than just adding another pulsar to the catalog. This object became a premier laboratory for testing the very fabric of gravity. Einstein's theory of general relativity makes specific predictions about how such a massive, fast-orbiting system should lose energy and spiral inward, emitting gravitational waves. The pulsar's incredible timing stability, now that its orbit was understood, allowed scientists to measure the orbital decay with exquisite precision. Each tick is a checkmark against Einstein's equations, a verification conducted in one of the most extreme gravitational environments we can observe. Finding this hidden clock in old data did not just reveal a new object, it gave us a new instrument, one that allows us to listen for the subtlest whispers of space-time itself and confirm that even in a frantic orbital waltz, the universe keeps perfect time. Even a world shrouded in perpetual cloud has its own rhythm if you know how to listen across decades. Venus, our scorching sister planet, is veiled in a thick, toxic atmosphere of carbon dioxide and sulfuric acid clouds that whip around the planet at hurricane speeds, completing a full circuit in just 4 Earth days while the planet itself rotates slowly beneath. This super-rotation is one of the great mysteries of planetary science, and for years our snapshots of it seemed chaotic, a churning, featureless hellscape. But by stitching together image sequences from 2 very different eras, the pioneer Venus orbiter of the late 1970s and the European Space Agency's Venus Express mission in the 2000s, scientists have uncovered a hidden metronome in the chaos. They returned to the archives of both missions, aligning thousands of ultraviolet and infrared images that revealed the cloud top patterns. By treating this 40-year visual record as a single, continuous dataset, a subtle, repeating structure emerged from the global hurricane. It was a massive, wave-like pattern in the clouds, a dark, elongated filament thousands of miles long that appeared, dissipated, and reliably reappeared in the planet's mid-latitudes every 4 to 5 Earth days. This was not a transient storm, but a planetary-scale atmospheric wave, a standing feature locked in a delicate dance with the planet's surface topography below. The identification of this long-term pattern is a revelation. It acts as a fixed reference point in the otherwise frenetic super-rotation, allowing scientists to measure wind speeds and directions with new precision over decades. More importantly, its very existence tells us that the surface of Venus, with its towering mountain ranges like Maxwell Montes, is actively talking to the clouds 60 kilometers above. The wave is likely a gravity wave generated when the super-rotating lower atmosphere slams into a mountain, sending a ripple upward through the cloud decks like a stone tossed into a fast-moving stream. This proves the atmosphere of Venus is not just a disconnected, high-speed shroud, it is a deeply coupled system. The planet's slow, solid body is still pushing back against its runaway sky, leaving a ghostly fingerprint in the clouds that patiently waited for us to connect the dots across 2 generations of spacecraft. The quiet heart of our galaxy holds the memory of a forgotten cataclysm. For years, astronomers have known that Sagittarius, a star, the supermassive black hole at the center of the Milky Way, is a relatively placid giant today, a faint radio whisper compared to the brilliant quasars in other galaxies. Yet scattered clues in the data, gathered over decades by different telescopes, began to tell a different story, one of a violent past. The evidence was not in a single image, but in the faint, lingering echoes of an event that reshaped our galactic core. Researchers returned to the archives of X-ray observatories like Chandra and XMM-Newton, studying the diffuse glow of hot gas that fills the space around the black hole. They also combed through radio maps, looking at the structure of strange, glowing filaments that stretch for light years above and below the galactic plane. Independently, these datasets were puzzling, but when layered together, a pattern emerged. The X-ray maps revealed enormous, symmetric bubbles of hot gas extending tens of thousands of light years from the galactic center. Meanwhile, the radio observations showed that massive clouds of molecular gas near the core, clouds that should be cold and dark, were instead strangely ionized, their atoms stripped of electrons as if blasted by an intense, sudden flash of energy. These were not random features, they were the scars of a titanic eruption. The leading theory is that several million years ago, Sagittarius, a star, experienced a dramatic feeding event. A large cloud of gas, or perhaps a star, ventured too close and was torn apart. As this material spiraled into the black hole's accretion disk, it did not go quietly. A portion of the doomed matter was channeled into two opposing relativistic jets that shot out from the poles of the black hole at nearly the speed of light, inflating the gigantic X-ray bubbles we see today. At the same time, an immense flash of ultraviolet and X-ray radiation exploded from the core, washing over the surrounding gas clouds and ionizing them in an instant, an effect that has lasted for millions of years. This was a light echo, a fossil imprint of that ancient flash still readable in the present-day state of the gas. Estimating the timing comes from measuring the current expansion speed of the bubbles and the distance to the ionized clouds, pointing to an event that occurred roughly 3.5 million years ago. In cosmic terms, this is a recent event, well after the dawn of humanity's earliest ancestors. The impact of this outburst was profound, though distant from our own solar system. It would have sterilized any habitable worlds in its direct path and fundamentally altered the chemistry and energy balance of the galactic center for eons. This discovery, pieced together from archival whispers, transforms our view of the Milky Way's heart. It is not a permanently sleeping giant, but a periodically stirring one, capable of waking to reshape its own domain on a staggering scale. A reminder that even our quiet galactic home has an explosive history written in light we are only now learning to read. Mars does not travel alone. For over a century, we have known that Jupiter is accompanied by vast swarms of asteroids, called Trojans, that orbit in stable gravitational pockets 60 degrees ahead of and behind the giant planet. These celestial hitchhikers are held in place by the balanced pull of the Sun and Jupiter. But does a smaller, rocky world like Mars have its own entourage? The answer was hidden in decades of wide-field sky survey images, the kind taken to map galaxies or track near-Earth objects. The challenge was finding something so small and faint against the dense backdrop of stars. Recently, a dedicated digital hunt was launched, applying new motion detection algorithms to this vast archive. The software was tasked with a specific search pattern, looking not for objects moving in random directions, but for tiny specks of light drifting across the star field at the precise orbital speed of Mars. It was a cosmic game of Where's Waldo, with the entire solar system as the backdrop. The patient, systematic search paid off. The algorithms identified several new asteroids, small and dark, perfectly synchronized with the red planet, nestled in those stable Lagrange points ahead of and behind it in its orbit. These are the Trojans of Mars. Their existence alone is a marvel of celestial mechanics, proving that these stable gravitational niches can be occupied around a planet with only a tenth of Earth's mass. But their true significance lies in their origin story. Are they simply captured asteroids, wanderers that stumbled into this stable parking space billions of years ago? Or are they something far more primordial? Their spectral signatures, gleaned from follow-up observations, suggest a composition similar to a class of meteorites known as C-types, which are rich in carbon and water-bearing minerals and are thought to be among the oldest, most unchanged materials in the solar system. This raises a tantalizing possibility. These Martian Trojans might not be random captures, but survivors from the very formation of the inner solar system, pristine building blocks that were gently swept into this stable zone as Mars itself was assembling. They could be untouched time capsules, preserving the original chemistry of the inner solar nebula in a way that no asteroid in the main belt, which has been battered and heated for eons, ever could. This makes them priority targets for future robotic missions. Reaching a Martian Trojan would be a feat of precise orbital ballet, but the scientific payoff could be immense. A spacecraft could visit a world that has been in a stable, cold storage orbit for over 4 billion years, sampling material that tells the unaltered story of our planetary beginnings. They are not just celestial curiosities, they are potential libraries holding volumes of our solar system's first chapter in their rocky pages, waiting silently in the gravitational shadow of their planetary host. A river of stars flows silently through the galactic night. This stellar stream, a long, graceful arc of suns all moving together through the Milky Way's halo, was identified years ago as a coherent structure, a beautiful but puzzling feature. We could see its present shape, a luminous trail against the dark, but its origin was a mystery. Where did this river come from, and what story did its current course tell? The answer required a kind of cosmic genealogy, a way to trace the ancestry of these stars back through billions of years. This became possible only by merging two very different archives: the brand new, precise motion data from the European Space Agency's Gaia mission with the old, chemical fingerprints stored in decades-old spectroscopic surveys. Gaia provided an unprecedented three-dimensional map, showing not just where these stream stars are, but exactly how they are moving through space. This gave astronomers the present-day velocity of the river. The older spectroscopic archives held a different kind of clue: the detailed chemical composition of those same stars, like a DNA test written in light. Each star retains the elemental signature of the cloud from which it was born. Stars born together in the same stellar nursery, and certainly in the same dwarf galaxy, share a distinct chemical pattern, a family resemblance in their proportions of iron, magnesium, and other elements. By cross-referencing the Gaia motions with these chemical fingerprints, researchers performed a remarkable piece of celestial detective work. They confirmed that every star in the stream shared that unique chemical DNA, proving they were all siblings born from the same parent cloud. Then, using the precise velocity data from Gaia, they ran the cosmic clock backwards in a supercomputer simulation. They calculated the gravitational influences of the Milky Way over billions of years and wound the stellar river's motion in reverse. The scattered stream of stars began to coalesce, their paths converging not onto a point, but into a tight, swirling cluster. The simulation revealed the ghost of a galaxy. The stream was all that remained of a small dwarf galaxy that had ventured too close to our own Milky Way, perhaps 8 to 10 billion years ago. The Milky Way's immense gravity acted like a cosmic tide, stretching and pulling at the smaller galaxy over successive orbits. Unlike a single star that might pass through unharmed, a galaxy is a loosely bound collection of millions of stars, and those tidal forces proved irresistible. On a timescale of eons, the dwarf galaxy was completely unraveled. Its stars were not destroyed, but were gently stripped away, smeared out along its original orbital path to form the long, thin stream we see today. The progenitor galaxy itself ceased to exist as a coherent structure. Its identity dissolved into the halo of our own galaxy. This archival synthesis does more than just solve a puzzle. It gives us a direct window into the Milky Way's growth and its ancient, violent interactions. The chemical signature tells us what that lost galaxy was made of, and by extension, what the early universe was like in that corner of space. The orbital reconstruction tells us when the merger happened, adding a precise chapter to our galaxy's autobiography. This stream is not just a celestial accident, it is a fossilized record of a long-completed act of galactic cannibalism, a testament to the fact that the majestic spiral we call home was built, piece by piece, from the remains of countless smaller neighbors. Its story, fully told only by connecting new maps with old starlight, reminds us that every structure in the sky holds the memory of its own creation, waiting for us to learn the language to read it. A brilliant flash on the moon's dark side was captured by amateur astronomers and professional monitors alike, a sudden spark against the silent gray. For years, that video clip sat in an archive, catalogued as a confirmed meteoroid impact, its energy calculated using the standard formulas of the time. The initial estimate suggested a strike from a rock roughly the size of a grapefruit, releasing energy equivalent to a few hundred kilograms of TNT. It was a notable event, but one of many in a constant, silent bombardment. Yet something about the data did not sit right with a later team of planetary scientists. When they revisited the high frame rate video, they applied a new generation of photometric tools, algorithms far more precise at measuring the true brightness, duration, and thermal radiation of that fleeting point of light. The reanalysis told a different story. The flash was not merely bright, it was intensely hot and lasted a fraction of a second longer than previously thought. These subtle details, once missed, were critical clues. The revised metrics pointed to a much more energetic impact. The object was not grapefruit-sized, it was closer to the size of a large beach ball, and the energy released was revised upward by an order of magnitude comparable to several tons of TNT. This was not a routine ping on the lunar surface, it was a significant explosion. The recalibration of this single event sent ripples through the field of planetary defense and lunar exploration. If one impact had been so dramatically underestimated, how many others in the historical record were also more powerful than we thought? This forced a reassessment of the entire impact flux model for the Moon. The estimated frequency of strikes capable of creating hazardous secondary debris fields, or even small seismic shocks, had to be adjusted upward. For the architects of future lunar bases, this is not an abstract statistical tweak. It is a vital engineering parameter. Knowing how often and how powerfully the lunar surface is struck informs everything from the required thickness of habitat walls and radiation shielding to the placement of critical infrastructure like power plants and landing pads. A module designed to withstand the previously calculated once-in-a-decade impact might need to be reinforced for a once-in-a-5-year event. The reinterpretation of that old flash transforms it from a celestial curiosity into a foundational data point for human survival off-world. It proves that our plans for a permanent presence on another world must be built not just on dreams, but on the most accurate possible reading of its environment, a reading that is constantly being refined by looking back at what we thought we already knew. The universe's most energetic particles carry a whisper of their origin in their direction of travel. For over a decade, the Pierre Auger Observatory in Argentina has been collecting these messengers, ultra-high-energy cosmic rays that strike our atmosphere with the force of a well-thrown baseball, creating a cascade of secondary particles that spread across kilometers. The observatory's vast array of detectors logged millions of these events, amassing a colossal archive of arrival directions and energies. The initial expectation was that these particles, having traveled across unimaginable cosmic distances, would appear perfectly random, scattered evenly across the sky like rain on a windless day. Their sources, theorists believed, were so distant and their path so scrambled by intergalactic magnetic fields that any trace of origin would be utterly erased. The data was processed with this assumption in mind, and for years the cosmic ray map seemed to confirm it, a uniform speckle of points. But a deep and patient reanalysis, applying more sensitive statistical tools to the entire decade-long dataset, revealed a subtle pattern hidden within the apparent chaos. The distribution was not perfectly uniform. There was a faint but statistically significant anisotropy, a slight excess of these ultra-high energy events coming from a broad region of the sky, and a corresponding deficit from another direction. It was an asymmetry so slight it had been buried in the noise, like detecting a single consistent breeze in a turbulent storm. This was a profound clue. The magnetic fields of our own Milky Way galaxy are strong enough to bend the paths of lower-energy cosmic rays into complete confusion. But particles at the very highest energies, carrying billions of times more power than those produced in our largest particle accelerators, should be stiff, resisting the gentle curves of galactic magnetism. If they still show a directional preference on the sky, it suggests two remarkable things. First, they are likely coming from beyond our own galaxy, from the vast intergalactic void. Second, their sources, while still mysterious, cannot be evenly distributed throughout the cosmos. That faint hotspot in the data points toward a particular direction in the extragalactic landscape. Researchers compared this directional hint with maps of known celestial structures, like the local supercluster of galaxies or powerful active galactic nuclei. While no single, blinding source emerged, the anisotropy aligns broadly with an area of the sky richer in nearby galaxies and large-scale structure. This implies that the accelerators of these incredible particles are not scattered randomly, but are somehow associated with the densest concentrations of matter in our cosmic neighborhood. The discovery transforms these cosmic rays from mere random bullets into faint signposts. Each one that arrives is now a tiny piece of evidence in a vast forensic case, its trajectory a blurred but readable line pointing back, however faintly, toward the most powerful engines in the nearby universe. It suggests that with even larger datasets and sharper analysis, we may one day trace these energetic ghosts not just to a region of the sky, but to specific galaxies, quasars, or even cataclysmic events we have yet to name. The quiet asymmetry in an old archive is the first hint of a cosmic roadmap, written in particles that have crossed the void between galaxies to tell us where they began. This quiet revolution in how we look at the universe reveals a deeper truth about science itself. Discovery is not a single event, a triumphant shout in a moment of clarity. It is a continuous conversation, a patient dialogue between our questions and the data we have already gathered. The stories we have explored, from the overlooked planet to the galactic cataclysm, are not isolated accidents. They are the direct result of a powerful news cycle, one where our existing archives are no longer just a record of the past, but a living, breathing resource for the future. Every time a researcher applies a sharper algorithm, a new theoretical model, or simply a different perspective to an old dataset, they are not repeating work. They are asking a new question of a silent witness, and sometimes that witness has been waiting decades to answer. This iterative process is powered by a remarkable synergy. New technologies like artificial intelligence and advanced computing give us the eyes to see patterns we were once blind to. Collaborative reanalysis, where teams across the globe share methods and challenge assumptions, provides the collective intellect to interpret what we find. But at its heart, this engine is fueled by simple, relentless curiosity, the willingness to look at something everyone else has seen and wonder if there is more to the story. This approach represents the ultimate maximization of our past investments. Every billion-dollar mission, every night of telescope time, becomes a gift that keeps on giving. The data it returns is not exhausted by the initial paper published. It is a seed that can grow new insights for generations, guiding our next giant leap by telling us precisely where and how to look. So as we stand today, surrounded by petabytes of data from Hubble, Kepler, Cassini, and countless other explorers, we must ask a thrilling question. What else is hiding in plain sight? The next Earth-like world, the signature of a phenomenon we have not yet named, the clue to a cosmic mystery we have not yet even thought to ask. All of these could be waiting, encoded in the silent streams of ones and zeros we have already collected. The frontier of space is not only ahead of us in the distant stars we have yet to reach, it is also behind us in the treasure troves of information we have already brought home. The journey of discovery continues, and it invites all of us to stay curious, to look closer, and to remember that the universe's greatest secrets are often the ones it has already whispered, if only we learn how to listen.